Okay, this is tutorial number 8. So the question is quite simple. So we have 1/7 power law, turbulent velocity profile, and the Blasius resistance equation is given as this one. Okay, so it gives you two. So in this situation, actually, you need to know which one that you want to use. Both of these equation is actually correct. So you need to choose one of them. Then you equalize with the shear stress that you get from von Karman. So tau is equal rho u square d theta dx. Okay, and then in this question, actually, the question want to ask you about the 1/7 power law. So mean 1/7 power law here is actually y over delta with the power of 1/7. So means that if you don't know what is the velocity profile of 1/7 power law, so means you cannot solve this problem. Sometimes on that time, there are students who equalize this value and this value because they have no ideas to start the calculation. So I already discussed this in tutorial, so I could make it faster here. So we know that 1/7 power law is this term. So and then from the question, we know that the Blasius resistance value is this term. So and then we calculate the value of theta here, which is 7/72 delta, and this is the von Karman equation substituted with the value of delta here. So and then we equalize with the Blasius resistance value here, and we could get the value of delta, so which is 0.3721x over Reynolds number to the power of 1/5. So and then we could get the value of theta. So we just substitute the value of delta here, and then we could simplify it into 0.036x over Reynolds number to the power of 1/5. So and then this is what I said. Okay, if you see this calculation, so we know that the CD is actually come from this FD is equal to CD 1/2 rho AU square. So and then if we manipulate this, rearrange this equation, we could write the value of CD is like this. So means that the value of the integration here is actually reflect the value of drag force. So what we do is we substitute with the von Karman because shear stress here can be calculated by using von Karman, and the BDX here is reflect the the surface area. Okay, please make some revision in the fluid mechanics one. Okay, so because we know that if we have a plate like this, so and then when the wind blows, so there are resistance occur to the viscosity that stick on the surface. That's why we need to multiply the total area here with the shear stress. Okay, that's it, the idea. So and then if we integrate this term, so if we integrate this term, so because it is, we could cancel the value of dx here. So and then we are integrating the d delta. So we could bring all the terms. So mean the rho here, the u and the b here is actually didn't have any relation with theta. So we bring it out here. So and then we are doing integration of d delta. So I'm sorry, d theta, and then actually the integration of d theta here is actually the integration of 1 times d theta. So you know if you have 1 dx, so you will get an x. So means that we will get a theta here. So and then means that if we solve this one, we could get theta over 1/2L. So means that we could simplify that answer as 2 theta over L. So we substitute the value of theta that we have previously. So finally, we could get 0.072 over Reynolds number to the power of 1/5. So here, what you could do is you could calculate the value of CD by using this equation 2 theta over L. So the terms L here is actually equalized with X. So let's say we have a plate like this. So this is the length of the plate. So the length of the plate is sometimes referred to L and sometimes referred to X. Okay. But in some textbook, they will say that the maximum length, so means if here is 0 and here is 5 meter, so sometime in certain textbook, they will write, so the L is equal to 5, but if you are talking to here, point at the middle or somewhere else, so it will write in X equal to 1 meter. So it's just sometimes the way they express the terminology in a boundary layer. But I hope you can understand that the L is actually showing the length, so the X also showing the length of the flat plate.